Okay, so welcome back to this second lecture on imaging in deconvolution, and I will speak about deconvolution. Okay, so in my previous lecture, I've been speaking about going from calibrated visibility to dirty beam and dirty image, and now we are going to clean beam and clean image. The key points about deconvolution is the fact that the measurement equation in the image plane is a convolution of the dirty beam times the intensity of the source times the primary beam. And the dirty beam in the inverse Fourier transform of your sampling function. And I've told you at the start of my previous lecture that because you have lost information because you don't have an increased sample UV plane, okay? And at the center, you don't have measurement at all. There is also a second reason why you have lost information is because you have noise, okay? At low signal to noise ratio, it will be very difficult to do something. So this has an important consequence. The important consequence is that it is impossible to recover the intrinsic source structure. Okay, you have lost the information. So you will not get the intrinsic source structure. Deconvolution is not what it's doing. And the reason why, let's assume that we have a solution of this equation. So here, S is for solution, not anymore for sampling. Okay, I've changed the notation. So I assume that S is a solution of this equation, okay? S being the product of B primary times I source. So E measured is equal to B dirty times convolved by S plus noise. So if I succeed to find another function R that when I'm convolving with a dirty beam gives 0, I get that S plus R is a solution because this is a linear equation, okay? So if S is a solution and R is a function that when it is convolved by the dirty beam is 0, gives 0, S plus R will be a solution. Are you telling me, yes, but it must be very difficult to find a solution R? But in fact, it's very easy to find a solution R, to find a function R that does this. You just take whatever function that has some value when you don't have measurement and 0 elsewhere. When you have measurement, you're putting 0 for R, and elsewhere, you're putting whatever you want. This gives you exactly this. Okay, property. So this means that there is an infinite number of solutions because I can choose whatever, for R, I can choose whatever value I want when I don't have sampling. Okay, you have an infinite number of solutions to a convolution equation because you have lost information. Okay? The goal of deconvolution is not to find the intrinsic source intensity. Is to find a sensible intensity distribution that is compatible with the intrinsic source one. And it's not possible if you're not making some assumptions. In order to deconvolve, you need to make some assumption on your source intensity distribution. Some a priori assumption. This is the deconvolution requirements. And this is what will define the class of deconvolution algorithm you're using. And of course, you need as much as possible knowledge on the dirty beam and the noise properties. Okay? If you had no knowledge on this, it would be hopeless. But in radio astronomy, both of them are very well defined. And again, the best solution is to have a Gaussian dirty beam, because in this case, you have no deconvolution at all to do. Okay? Unfortunately, it's difficult to have an exactly, with an interferometer, it's difficult to have an exact Gaussian dirty beam because there are plenty of constraints. Okay. So now I will present the family of deconvolution algorithm that is called clean. And clean makes the following assumption, a priori assumption: the source is a collection of point source. And the way the algorithm is working, it's a matching pursuit. So let's see it on an example to explain it. So this is a suit experiment where we have, in one dimension, we have the intensity in the flux in Jansky as a function of position on sky, one-dimensional because it's much easier to understand. And let's assume that the intrinsic sky intensity is made of 2 point source, one at 2.5 Jansky at this position, and one of 5 Jansky at this position. Okay? Now, that's not what we observed with an interferometer. What we observe with an interferometer will be the convolution of this by the dirty beam. So here, let's take the dirty beam, a typical dirty beam, that is this one, in one dimension. That's a black curve. And you see that you have the main lobes and some side lobes. Okay? And the first thing that we do when we're cleaning a dirty image is that we are imaging the dirty beam and we're making a fit of the main lobe, a Gaussian fit of the main lobe, with the hope that the Gaussian fit will fit well the main lobe, which is the case here. Okay, so what is the dirty map? The dirty map is a convolution of the 2 point source by the dirty beam. So when you have a point source, you just multiply, it's a Dirac, so you just multiply your dirty beam at the position of the point source for the first one. So the peak will be 2.5 here. And for the second one, you multiply the point source, the flux of 5 Jansky by the dirty beam, and you add it. You add both. And this gives you the dirty image. So when you are initializing your cleaning component, you start by renaming the dirty image as residual map. Just a renaming for the moment. You will see why in a minute. And you create another buffer that is called a clean component list, where we find point sources. We will put the flux of the point source at the right position. Let's do it. First, we need to localize a first point source. In order to do this, we're localizing the maximum of the residual map. So the maximum of the residual map is 5 Jansky at these positions. And we say, good. We have found one point source. And we are putting it in the clean component list at the same position. We are pointing 5 Jansky. And then we will subtract the contribution of this point source to the residual map. So the contribution of this point source to the residual map is just the multiplication of this point by the dirty beam, because this point source is a Dirac, and we subtract it, and we end up with 0. Okay? And that's easy. We iterate. Localizing the second maximum, we find a point source of 2.5 Jansky at this position. We put it in the clean component list, and we remove it. We remove the contribution from this point source to the residual map. So we are multiplying the flux of this point source by the dirty beam, check, and we subtracting, and we get 0. So easy. So, in fact, it's slightly more complex than this, because first, the position of the source is not very well defined, because in the dirty image, you have a pixelized image. And so you will assume that the point source is localized at the center of 1 pixel, which there is no reason why in nature it should be. So there is some uncertainty on the position of your point source. And in order to avoid this, we regularize the solution. And so the clean component list, we will convolve it by the clean beam, the synthesized beams that we have been fitted at start of the process. Okay? And what you will say that this red curve, the clean component list convolved by the synthesized beam is the clean image. Okay? Okay. That's a simple case. Everything is working very, very easily. Let's now make an example that is more complex. Not so much more complex, just 2-point source. Again, 2-point source, but this time they will have the same flux at those positions, 5 Jansky and 5 Jansky. So let's try to make the dirty image. So we are keeping the same dirty beam. We are convolving those 2-point source with the dirty beam. So we are multiplying the first point source and by the dirty beam shape, and we're getting the pink curve, and the second point source convolves the flux of the second point source multiplied by the dirty beam, give you the cyan curve here. And you just add to get the dirty beam. And that's the dirty beam is the black curve here. You see that something happened. Instead of having 2 peaks of 5 Jansky, now you have 2 peaks of slightly more than 6 Jansky. Why is it? It's because in this experiment, the sources are localized in a way, on purpose, it's a suit experiment, that the side lobes from one of the sources is localized at the position at another source. So this modifies the flux, the maximum of your dirty image when this happens, and this happens all the time. Okay, but we will do exactly the same as before. We're starting with the residual map, where the clean component list that is empty, and we will localize the maximum. I found 1-point source at these positions. 6, slightly more than 6 Jansky. So you see that the source that we found, we have just found, is slightly brighter than the actual one. We are subtracting from the residual map the contribution of this source to the residual map. So we are multiplying the flux of this source by the dirty beam shapes with subtracting. Okay? And we iterate. So now we are finding again the maximum. The maximum here is at this position, and it's about 4.7, so slightly less than 5 Jansky. So the second source is at the right position here, but it does not have the right flux either. Okay? So now you're using this point source, and you're subtracting from the residual map its contributions by multiplying the flux by the dirty beam, subtracting, and then you end up here. And then that's where the problems start. Because in this experiment, there is no noise, but in general, there is noise So in your residual map, at some points, you don't know whether what remains is noise or signal. So let's assume that as the first time that we don't know and that there is some noise of this level. And so we say, we should stop. Okay, we should stop convergence. So what we do is we regularize the solution by convolution with the synthesized beam, and we say, okay, this is our solution. This is the clean image. But as this is the source experiment, we have the actual sky distributions. So we can take the actual sky distributions, convolve it with the Gaussian, and subtract it from this solution. So this is the clean image minus the actual solution we should have. And we see that there are differences. Okay? So the solution didn't converge. Okay? We didn't find the right intrinsic solution on sky. And you see that the RMS of the difference between the clean image and the actual sky distribution is 0.21 Jansky. One more comment. I forget right now about the primary beam. Okay. I assume that there is no primary beam. Okay. So this means that if you're doing a too superficial cleaning, you will get only approximate result. On the other hand, because you have noise, if you're doing a too deep cleaning, there is a risk at some point that you will amplify the noise because deconvolution is a non-linear process, and you will create structures. So the actual question is, how do we know that we converge or not? Okay. In fact, we can do first order correction. Let's restart here. So let's restart here. Okay. I have the clean component list regularized, convolved with the synthesized beam, and I have the residual map. One thing I can do is add the residual maps to the regularized list of clean components. And this makes a first order correction. Okay? Here I have added to the clean component list regularized the residual map, and you see that the peak of the two main sources now are closer to 5 Jansky. Okay? But it's not perfect because here you see that you still have some irregular baseline. We can compute the difference between the clean image, that is the addition of the regular clean component list and the residual map, and the actual sky distribution, and we get this. So it's not perfect, but we see that the RMS decreased a lot from 0.21 Jansky to 0.08 Jansky. So it means that by adding the residual to the regularized list of clean components, you're improving quite a lot the solution when the convergence is not reached. In addition, because the noise remains in the residual maps, by doing this, you end up with a product on which you will have the noise property, so you will be able to measure the noise and to know whether you have a detection of 5 sigma, 6 sigma, or so. Okay? Or very high signal to noise ratio. Okay, this is the first little secret of clean algorithms. You need to add the residual maps in order to do a first order correction when your cleaning didn't converge. There are others. The second one is related to what we did. We added the residuals to the clean component list. This makes a first order correction, but it works only at one condition. Only when you're not doing super resolution. Okay? Super resolution is, I'm doing cleaning and I'm clever. I'm so clever that I will not use as the regularization beam the beam of that I fitted, the natural synthesized beam of my experiments. I will use a smaller one. That way, I get a better angular resolution. Well, so here, instead of using to regularize the clean component list, instead of using the cyan curve, let's assume that we're using the pink curve. Okay? Well, when you're adding the residual, when you're adding with the science curve, you have the natural synthesized beam, you get a first order correction. But when you're doing super resolution, you see that you get strange things happening, negative stuff happening, okay? So that's why super resolution is not recommended. And this is due to the fact that by adding the residual, in the residual, you have a natural angular resolution. And by adding the residual, you should be consistent between your clean component list and your residuals. Another little secret. People always think that, and they are right, the intensity measured, its energy, it should be positive. Okay? So because it should be positive, we should forbid for negative clean component. Okay? That seems so obvious. But that's wrong. That's wrong. Let's authorize negative clean components. So instead of localizing the maximum of the residual, now we will localize the maximum of the absolute of the residual. So here, the maximum of the absolute residual will give you a point source at this position that has negative flux. Okay? It's a clean component. So we add it at this position. So this is the same position as the first point source we have found. But instead of adding the flux positively, we are making a first order correction. And we see that we end up from Szymanski to almost 5. Okay? And then from the residual, we are subtracting the contribution of this clean component to the residual map. So we're multiplying the negative flux by the dirty beam. We are subtracting, and we see that on these positions, we have made quite a good correction. Okay? So negative clean components are needed to improve your solution. Okay? And we continue. So we are localizing the maximum of the absolute of the residual map. Well, here it's positive. We are adding it at the position we're finding. So it makes a second order correction, a first order correction to your second clean component, and you're getting closer to 5 Jansky also here. And then you're subtracting the contribution of this clean component to the residual map. You're multiplying by the dirty beam. You're subtracting, and you end up here. And then, in these two experiments, we didn't converge, but we know that there is noise. So we say, okay, let's stop. So we regularize the clean component list by the synthesized beam. We're adding the residuals. And again, this is the clean image. This is the clean image. And again, we can subtract, because this is the suit experiments, we can subtract the actual sky distribution at the resolution of the experiment. And we see that it's almost 0 now, the difference. And we see, and in fact, the RMS decreased by more than 1 order of magnitude. Okay? So having negative clean components is required if you want to converge. Okay? So this is a summary of the algorithms. I won't redescribe it, I'll just did it. The only thing I will say is that one thing I didn't say up to now is that when we identify the position and the flux of the absolute of the maximum of the absolute of the residual, in fact, I've told you that we are using this flux to put it in the clean component list. In fact, that's not what is done in the algorithms. We are putting only a fraction of this flux, typically 20%. Okay, this helps the convergence. And in fact, you can show that the algorithms will actually converge only if we're approximately this range of gain, so between 10% and 30%. And In Gildas, we are using 20%, and myself, I never change this parameter. So now the next question is, when do you stop cleaning? Okay. So there are a number of criteria. So the first, let's use this one as the first criteria. The residuals are less than a fraction of the noise. In radio astronomy, you can have a good idea about the noise level, and you say, okay, when I don't want to clean too much, too deep the noise. So when the noise level, when the residuals are lower than a fraction of the noise, maybe 0.5, 50% of the noise level, I will stop. This is one possibility. A second possibility, this possibility is nice. The first possibility is nice when you have an experiment that is limited by the thermal noise of your interferometer. That's not always the case. Sometimes you have, well, you always have phase noise, and phase noise is scattering the flux of point sources around these point sources. So it's not thermal noise in the normal sense, but it added some flux, it scatters the flux into a collection of point sources around your very big point source. And this will limit the intensity dynamic of your image, okay? Because instead of having the thermal noise, because you have a very bright point source, the phase noise will dominate around this bright point source. So when this happens, we are said to be dynamic limited, and then it is advised to use another criteria, that is the residual, the absolute value of the residual, the maximum of the absolute value of the residual should be less than a fraction of the initial dirty beam maximum, because the initial dirty beam maximum should be the very strong point source, and this should be a good criteria. This can be discussed a bit, because today with NOEMA, we can do fast self-calibration, and fast self-calibration should solve the problems of dynamic limits. And you should be able to almost get the noise that is compatible with theoretical noise. The measured noise that is compatible with the theoretical noise. Sorry. So another way to stop convergence is say, okay, I won't use any of those two criteria, and I will use a number of clean components, and I will stop when the flux that is formed is flat. We will show this in a minute. And in order to do this, you're fixing the number of clean components. And then you can try to play with all three criteria if you want. I suggest to be simple and use one of those criteria at a time. Another secret is that by default, we are only cleaning the inner quarter of the dirty image, at least for single pointing image. And finally, you can use a support to define a support, a mask in your image, saying, okay, I will help you, and you should search clean. You should search for the next clean component inside a region that I define myself. Okay, and why it would help? It's because it's giving a priori information on the localization of your source. Okay. Of course, this is an a priori information only if that's true. If you're making a mistake in defining your support, and there is solution outside your support, you will bias your solution. Let's see it. No? Yes. So here I'm showing the dirty beam, the dirty image. The cumulative flux as a function of the clean component number. So at start, I found the flux is increasing very fast, and then it's saturating. And when I arrive here, I say, okay, this is one way to know that I have been converging. Okay, the flux is almost flat. This curve, the cumulative flux, become flat with a high number of clean components. Another way, so then you have the residual. Another way to know that you have converged is that the residuals look like noise. Here you have the list of clean components that has been regularized with the synthesized beam, and here you have the sum of the two, which give you the clean image. Okay? No support yet. So when you're defining sometimes people try to define support on dirty image. Well, from my viewpoint, this is plain wrong, okay? Because you don't know where the source is. So in fact, mapping by default will not authorize this. It will authorize you to define a support only once you have done a first clean image. Here it's just a zoom. Okay, I'll zoom the inner quarter because I've just told you that the clean algorithms is only cleaning inside the inner quarter. So we see it very clearly here. Okay. So here it's just a zoom, exactly the same image, but zoom. And so here you see, well, it's not very clear, but you see that it looks like noise. Okay, there is no structure on your image, so you have converged in this case. Let's make a support. So let's define a support like this on this clean image and see what is the impact of the cleaning process. So before support, after support. So the first thing you can note is that the cumulative flux curves becomes much more regular. Okay? It's less oscillating. Why is this? It's because you have to help these algorithms by telling him you should not search for clean component here, which will make you oscillate here. You should search only where the signal is. So this is true information. That's correct. Now, this is an obvious example. But let's assume that we made a mistake and we define a support only on the lower part of your source. Okay? So you see that we screw up completely your clean image. Okay? Of course, this is a caricature, but this is to let you understand that a support that is wrong will bias your clean image. And you see that your clean component curve has a strange behavior, and that in the residual you still have a signal. Okay, that's an obvious example. What happens in reality is that you have a point source outside your support that is not so bright. Should you put it inside your support or outside? Well, you should put it inside your support, but how do you know that this is the true source? Because you have the noise level and it's 5 sigma or 3 sigma. So when I was young, well, people, in general, when people are defining support, there is a tendency to say, okay, I want to define it very precisely where it's positive here. But that for sure, if you're doing this, everything that is at signal to noise ratio of 3 or less than 3, you will exclude it from your support. So when I was young, when I arrived at IRAM, I was doing this. Okay, and then I studied a source for 10 years, and at some point the instrument improved, and I increased the signal to noise ratio. And one source that was, it's not on this case, but there was one point source outside the support I was doing that was always there at 3 sigma. So I thought maybe it's something, so we integrated longer, and in fact, it was a source. Okay, so for several years, I've been confused between noise and source. So now that I'm growing older, I'm using less and less support. Okay, by default, I'm not using support, And if really the algorithms does not succeed to converge, then I'm trying to think. There are different invariants. So the first one, the one I've shown you, is the Hawk-Bomb. This is a very robust algorithm. Then you have two faster search algorithms that are called Clark and MX. And the idea is that instead of localizing one source at a time, you will localize in your residual map several ones, a given number. And you will, this is a minor cycle, and then you will subtract it all at a time. This is doing less computation. Okay, so this is faster. For Clark, the subtraction is done in the image plan, as we did in the previous example. In MX, the peoples, so this is Cotton and Schwab, said, okay, imaging is gridding is making plenty of artifacts, so we have a collection of point source. We will subtract it directly from the visibilities, and we reimage. And that way, the artifact will be lower because the artifacts are proportional to the flux you have in your initial data. And so they are doing the subtraction on every major cycle in the UV plane and reimage. Because they reimage, this one is slower, MX is slower than Clark. The difficulty with the Clark and MX is when you have side lobes that are larger than 20 or 30%, then it has difficulty to converge. So that's why in mapping, by default, the default algorithm is Hawk-Bomb. You're sure that you will converge. Okay? Then when you have extended sources, you have two alternatives in mapping. One is called SDI, and instead of, for each maximum in the residual, it will not take just this one, it will take support around these residuals, assuming that if you have a strong point source and your source is extended, there is a large probability that you should take many point source around this one. Okay, so instead of using one point source, you're using a support around it, and that's what you're putting into your clean component list. The multi-resolution approach is different. Is stating you will make dirty image at different angular resolution. The one at largest resolution will be at lowest resolution will be more will have more signal to noise ratio to medium scale structures, and so you will choose on the residual. You will locate the maximum of each of the image you have been produced at different angular resolution, and you will say, I will choose the ones that are the highest signal to noise ratio, and this can be this resolution or this resolution, and I will subtract it from everybody. And we iterate it. MRC exists in mapping, but it's a too simple multi-resolution approach, so I don't, just for you to know it's there, but I don't advise to use it. A few recommended practice. You should save your time. So instead of trying to deconvolve 1,000 times your 4,000 channels, you should pick the one that has the highest signal to noise ratio. So you're making first image. In the dirty image, you're looking the one that has the highest, the channels that have the highest signal to noise ratio. You're extracting this one, and you're working only on this one in order to fine-tune your deconvolution algorithm. This one, as it has the largest flux, it will be the most difficult one to deconvolve. So if you succeed to deconvolve this, your recipe should be okay for every other channels. And then you're making it, once you're satisfied with these channels, you're making the same for every channels. You will save plenty of your time. So instead of spending days trying to deconvolve, you will spend days trying to do science. But also it will save, again, it will help to save the planet. So start with a bomb. If you're satisfied, if it works well, you're done. If not, then you can try the other algorithms. Start without support. If you're satisfied, stop. If not, think about it. And you can try to define some support. I would say that instead of trying to define a support of the clean image, you should try to think if you have a better strategy. For instance, if you're observing a GMC, the probability that the CO emission is located inside the H1 emission, the atomic emission of H, is very large. So if you have a good image of H1, you should use the support of H1. This will help and probably not bias your solution. If you have a very exotic molecule and you have a 12 CO image that is good, you can use the support defined on your 12 CO image for the molecule. It will help again, okay? So I advise to use a large enough number of iterations to ensure convergence. Let's say for a single field, let's start with, if you're doing a detection experiment, 100 clean component. If you're doing an image, let's start with 1,000. And then if you're stopping with the number of iteration, if this is your stopping criterion, there is no point adding one component after the other, okay? Just double the number of clean components. Go from 100 to 200. Is it converge? Yes, we are done. No, let's go to 400. Did it converge? Yes, stop. No, go to 800. And you will converge very fast to your solution, to the number of clean iterations that are needed. You should click down to the theoretical noise level unless there is a very strong source present. And in this case, you should do self-calibration, fast self-calibrations. And one thing that is important, in my view, is that your residual look like noise. And finally, you should consult an expert until you become one. Okay, so clean is has been around for 40 years. I think this is the 40th anniversary, in fact. No, 50th, 50th, 50th. I'm going older. But there are other tendencies in deconvolution. So people in the last 10 years, maybe 15 years, people have spoken a lot about sparsity. And the idea behind this is that for a point source, clean is a very sparse algorithm. A point source is described by 3 parameters. Okay, you have an image that are plenty of information into it. But if you have only one point source in your image, in order to describe your source, you don't need the image. You need 3 parameters: position X, Y, and flux of your point source. And you're done. This is very sparse. Okay. But of course, all the scale is not made of point source. So let's take the opposite view. Let's assume that you have a constant source. Okay? A constant source in the image plane needs many informations to describe it. You need the flux in all the pixels of your image. So you need a full image to describe it. But do the Fourier transform of a constant source. It will be 0 in the UV plane. It will be 0 everywhere except at the center. At the center, 0, 0, you will have the total flux of your point source, and you are able to define your your source with only one parameter in this case, because you already know that it's in 0, 0. Okay? So this is the sparse for a constant source. The sparse space is the Fourier plane. Okay? It's not the image plane. So sparsity just assumes that there exists one transform, phi, that going from the image plane to another space. That will make your source description sparse, and thus easy to describe with a few parameters. Okay, much less than the number of pixels you have in your initial image. This is an assumption. And the game of the role is to minimize, to find the intensity distribution that minimize the chi-square of your data, so the visibility minus the Fourier transform of your sky intensity. Again, here I'm forgetting about the primary beam, the detail. At the condition that phi I, the transform of I by phi, is sparse. How you're doing this? You're doing a Lagrangian minimization, so you're minimizing the chi-square plus a Lagrangian parameters times, for each pixel, the sum of the absolute value of phi I at the power 2, divide the everything divided by 1 over p. So this is a norm. This one is a norm L2, and this one is another norm that is called LP. And if p is 1 or lower than 1, the lower the value of p, the more sparse you will make your source. Okay, that seems very easy like this, but in fact it's not. Because there are lots of applied mathematical details. Which function phi should you use? Which value of p? Which minimization routines in order to ensure that this will converge and you will not be stuck into a local minimum? Which noise models? How to fix the regularization parameters, lambda? So there are lots of questions. That's why I assume not many people are still using this today. There is a new tendency in the last few years is to try to use, I don't have a slide about it, to try to use the neural network. That seems magical. But that's also some kind of black box. So you don't exactly know what you're doing. I think that's promising, but we need to understand better what's going on there. So to do those two first lectures, I need a lot. The two books, the Fourier transform and its application from Braswell, and the Radio-Astronomy book from Cross. It's a old one, but I think it's a pretty clever one. That's all for this lecture.